Yeah, right. It's a university. So my name is Vera Trainer. I'm the Marine Science Director here at ONRC, and it really gives me great pleasure to introduce our speaker for this evening. Thank you all for coming. He has such an interesting bio. I thought I would read a little bit of it. So he comes to us from the East Coast. He did his undergrad at Cornell. He majored in physics and he worked with astronomer Carl Sagan. So I thought this was about weather and not stars, but maybe he'll explain that. On a model of Martian atmosphere, and with Stephen Schneider of NCAR on climate modeling. His PhD then was from University of Washington, where he did his doctoral work on African wave disturbances, the forerunners of tropical storms and hurricanes in the Atlantic. And he's been involved in several initiatives, including acquisition of coastal radar here in Washington on the coast and improving the infrastructure of the Weather Service. He has a book that he wrote in 2008, Weather of the Pacific Northwest, and it's even in its second edition. He has a weather blog that you can Google and find. He's a full professor at University of Washington, is highly influential, editor of several journals, and he's a member of the Washington State Academy of Sciences, where I chatted with Cliff and said, hey, would you come out to Forks and give a talk? So this is it happening here. So thank you so much, Cliff, for being here.
You've been keeping the intro brief.
No problem.
That's a bet.
Might say, you came to the University of Washington about 3 or 4 years after I left.
Right. Yeah, so I gotta be careful. I gotta know who you're all.
Yeah, exactly.
So I can't get away with anything today. Okay, well, I gave a few topics I could talk about, and the one that was selected was one I've written several papers on, very interested in, and that's the great storms of the Pacific Northwest. So that's what I'm going to talk about today. All right, so let's get into it, and I'm going to leave plenty of time for questions, which I really like. Okay. Now, we don't get tropical cyclones and we don't get hurricanes here, but we do get Pacific cyclones, mid-latitude cyclones that can be pretty intense. I mean, we're talking about they can be as strong as category 2 or 3 hurricanes in terms of the wind speeds. Okay, and here's an example of one that I personally, and that is the Inauguration Day storms of 1993. Okay, just a little bit of terminology. We often call these mid-latitude cyclones, tropical cyclones, mid-latitude cyclones. The winds can exceed 100 miles per hour and sometimes more than that. And their energy source is the large change in temperature north-south. We call it the mid-latitude temperature gradient. Okay, so that's where they get their energy, which is different than tropical storms. Okay, well, we're on the coast here, and I think it was appropriate to mention that Native Americans in the Olympic Peninsula, they knew about northwest wind storms, and they had several legends about their origin. And one of them is the Thunderbird. Has anybody heard of the Thunderbird legend in this group? The Thunderbird. And the idea is that these strong winds were associated with this gigantic bird that lived in a cave up in the Olympics, not too far from where we are today. And when it went out to get its favorite prey, kill a whale, the wings were huge, big as a war canoe supposedly. And when it flapped the wings, you had very strong winds. Okay, so anyway, I thought that was kind of colorful. When the early European explorers got here, they knew something was strange going on. When they came in Strait of Juan de Fuca, looked around the Olympic Peninsula, they noticed that there were the evidence of strong winds. There were gigantic trees that were down. In fact, this is a quote from John Mayers in 1788, and he was off of Cape Flattery. Okay, I'll just read it. The force of southerly storms, and it was clear that the way the trees fell, the winds were from the south. The force of southerly storms were evident to every eye, with extensive woods being laid flat by their power, and all the branches going to the northwest. So it was very obvious that this place was hit by extraordinarily strong winds and from a certain direction. The early settlers out here, they rapidly figured out that there were some strong storms in the area. And for instance, pioneer Arthur Denny in Seattle, he noted that the heaviest windstorm since the settlement of the country occurred in 1875. And timber was down, structures were damaged. It was obvious that this place once in a while gets hit by these extraordinary storms. And the first one that really got written up to some degree, it's even in newspapers, was the Great Gale of 1880, January 9th, 1880. And this hit mainly the northern Oregon, a little bit of southwest Washington. Thousands, hundreds of thousands, probably tens of thousands of trees were knocked down. The winds were estimated to get almost to 140 miles per hour, okay, on the coast, and only 70, 80 miles per hour in the interior only, okay? Buildings throughout the Willamette Valley were damaged. The roof of the state capitol in Salem was blown off. And after that, some snow fell there, right, just to top it off. And the central pressure was 955 hectopascals. Now, I'm going to be throwing this pressure thing around. Okay, the central pressure of these storms, meteorologists are fixated on, is a measure of the strength of the storm. And the pressure unit we use is hectopascals. Okay, pascals are unit of pressure and hecto is on. So the sea level pressure is about 1,013 hectopascals. That's an average sea level pressure. Okay, just giving them. Anyway, so this was a big event, and it went right up there in Oregon. Okay, so this was a little bit south of us, but so this really got people's attention. But the next storm I want to talk about was an extraordinary storm that affected us up here, and that is the Great Storm, the Great Cyclone of January 1921. Okay, this is an intense storm that went up through central to northern Washington, and this brought the winds at North Head, just on the southern Washington coast, winds reached 126 miles per hour. There was at North Head, and the maximum 1 minute, so the gusts got to 150 miles per hour. At Tatoosh Island, not that far from here, winds got to 110 miles per hour. Tremendous number of trees were blown down the Olympic Peninsula. I mean, more than equivalent to a year's harvest. It was extraordinary. Here is a picture or an image that shows the percentage of blowdown during that storm. And it's not that far from here, folks. 40% blowdown. 40%. It's extraordinary. Okay, but it's a kind of limited area. And this was known as the Olympic blowdown storm. Quite an event. Now, here's an interesting question. Why? Why were the winds really, I mean, the winds were strong enough down here, right? I showed you 120 something miles per hour, right? But something even stronger happened here, right? What? Well, I've done some research understanding how the pressure pattern in the Olympics with various winds, and I can tell you the answer to this question. And that is the pressure pattern was like this. The pressure pattern, these lines are isobars, lines of constant sea level pressure. And I don't know if you can see them over here, and there was high pressure here and low pressure there. And why was there high pressure there, low pressure there? Tom knows, but what happened is the winds were from the southwest. So the air is supposed to rise on this side of the Olympics, and it's supposed to sink on this side of the Olympics. Well, when the air rises, it cools. Goes from high pressure, low pressure, cools, and cooler air is more dense, and that goes to the pressure rise. On the other hand, the other side, it's sinking. Yes, compressed, it's warm, it's less dense, the pressure falls. So when you have this pattern, you get high over here, over there. And that's why people live in Squim, right? Why do people retire there? Because the air's sinking there and they have about the same, the precipitation is about at Squim, it's about the same thing as in Los Angeles, right? The number one question I get, people calling me up from out of town, is they want to know about Squim. Because they want to know about retirement. Anyway, so it rises and cools, you get high pressure here, low pressure there. Well, between them is an area of large pressure change, right here. And the air accelerates when it doesn't apply the pressure, right? Squeezing the toothpaste tube, right? And you do that experiment all the time. And so you get the strong winds along the coast. By the way, another place you get some strong winds is here, right? And there's a story about that. I don't want to do that right now. But that's why the winds were absolutely extraordinary. They were probably 150 miles per hour plus. And that's what took down those trees. Okay. Well, if I really want to impress you, I'll tell you about the greatest mid-latitude cyclone that ever struck our region. Anybody know what it is? Who knows? Anybody know? No? The greatest storm to ever hit the Northwest. And it is probably the greatest mid-latitude cyclone that ever hit the United States in the last 100 years. Columbus Day, you got it. Okay. This is a well-informed individual. Okay, the Columbus Day storm in 1962. Okay. So if this storm hit today, it probably would cause the same path, it'd probably be $50 billion. Okay. Okay, let me tell you about this storm. So it's probably the strongest storm to strike the Northwest since the arrival of European settlers. And probably the strongest mid-latitude cyclone in the lower 48 in the last 100 years. Okay. Anyway, an extensive area from Northern California all the way up into southern British Columbia. Got it? There were sustained winds of 60 to 70 miles per hour all over the place, over 120 miles per hour on the coast. And just to give you this one had a death toll. 46 people died, 300 something had hospitalization. There was heavy rain within California, and the pressure was 955 hectopascals. So it's pretty deep, okay? And just to show you some pictures, here we are right there, okay? That's a pressure analysis. Those are isobars, lines of constant pressure. I mean, you've seen these kind of things, something you see on TV. So that's a very deep low sound. And it followed this track. Whoa. And notice there's a very intense difference in pressure there, right? Strong wind. Whoa. Yeah, not too far from here, folks, right? So this is the Columbus Day story. I know around here people think about timber, right? There was 10 to 15 billion board feet down, okay? Enough to build 1 million homes, okay? Okay, amazing. There was, 53,000 homes were damaged. I mean, the damage was absolutely extraordinary. The twin 520-foot towers that supplied power to Portland, look at that, okay? Long view, that got taken out. You really want to be impressed, is really heavy horse statue knocked over, right? Okay, it's called a circuit rider. Got toppled over, okay? But if you really want to be impressed, I'll give you nightmares. At Cape Blanco on the southern coast of Oregon, the winds hit 150 miles per hour, with gusts of 179 before the anemometer was tied. I mean, that's serious. The Mount Hebo radar facility was destroyed. And we had a celebration of this event, the 50th anniversary, and we had somebody who was there, who was in the Air Force, Mark Cole, and he talked about what it was like that night. He was there, okay, and he wasn't up there. So here's the question: how good were the forecasts? You think we nailed it the day before? I'm a meteorologist. I teach weather prediction, right? I wrote 62. What do you think?
Pretty tough.
Pretty tough. Well, the models weren't very good at it. The forecasters in Portland and Seattle, they knew there was something happening. You know, there was no ship as they knew. But the position was uncertain, the magnitude was uncertain. And the weather models of the day predicted something but not very strong, right? So if you look in the Seattle Times, the day before, you know, it was like, not much. In fact, they even had an article of, you know, if you're a hunter, it was a good day to bag your deer, you know. So it will, this is the, this is the actual, this is an actual chart produced by a forecaster. That's it. This is, this is 5 AM on the 12th, that's the day. And they knew there was a system there. They didn't have the amplitude. They didn't have very many observations, okay? And you had a general idea what was gonna happen, but you know, by that morning, they knew there was gonna be a storm, be damaging winds. They had no idea the magnitude. And 2 days before, they didn't know it at all. They kind of caught it that morning, okay? And, you know, and you know, and there it is, the storm coming up the coastline, okay? Again, the damage to trees were absolutely immense. I mentioned that already. And just to give you this, the winds that were observed around the region. I mean, Newport 138, Nebo 131, you know, 145 plus at Cape Blanco, 116 in Portland, you know, 81 at Hoquiam, and 100 at Renton. I mean, there's not much to say about Renton, Washington. But in this case, they had something to brag about, right? 98 dollars. By the way, one thing I want just to really impress you, you know, you hear about hurricanes in category 1, 2, 3, right? And this is it's called the Saffir-Simpson hurricane scale. This was equivalent to a category 3 hurricane. You know, 110 to 130 miles per hour, you know, that pressure, this is as strong as a category 3 hurricane. But it was worse than that. It was much bigger. These hurricanes are smaller than our storms. Okay. Here's a storm maybe you may remember. I remember this one. This is the Inauguration Day storm. You know, the day that President Clinton became president of the United States, right? In January 20th. That's the day. Okay. And the interesting thing is that this was the first storm to be forecast skillfully a few days before. Personally, something happened. Okay. But the thing is, the media weren't paying attention to it that day. But I remember this. I was at the UW, and I remember the winds gusted to 88 miles per hour that day. And I've been through hurricanes, and it was like it. So the Inauguration Day storm, just this is more recently mentioned, it was probably the third most damaging storm in the last 50 years. Columbus Day storm was number 1, and a more recent one, the Hanukkah Eve storm, 2006, and if you remember that. So the Inauguration Day storm, the winds got to 100 miles per hour. And along the coast here, 6 people died, you know, almost 1 million people lost power, you know, all these gee whiz things. So that was a big storm. But the winds weren't anything like the Columbus Day storm, 80 miles per hour, you know, that kind of stuff, 60, you know, that kind, you know, these kind of winds, okay? Was not equivalent, okay? But, and you can see here's the low, and it's coming up the coast, and I'll be talking about this. For us to get really strong winds here in Washington State, you want the low to come up the coast and cross over the Olympic Mountains or something like that. That's the sweet spot to get strong winds in Western Washington. Okay, the more recent one, and I'll just mention it very briefly, the Hanukkah Eve storm. Very intense storm. That's probably number 2. And that number of places winds gusting to 60 to 80 miles per hour in Western Washington. On the coast here, some places got to 100. I went to Mercer Island, where Mercer Island is, right near Seattle. Yeah, that's what it was like. I couldn't drive around Mercer Island. Yeah. Anyway, there's a lot of these storms. And this guy named Wolf Reed that's put together this collection. It's really wonderful. I've written a few papers on it. But he's talked about all these storms. So that, there's been quite a few of these storms. I gave you the big ones, but every year or two, there's a decent one that comes up the coast. Okay. Well, next, since I am a UW faculty, and I very wouldn't be happy unless I did something like this. I'll give you a little bit of Northwest Windstorm 101, okay? Hopefully I've impressed you. These things can be pretty amazing, okay? Okay, so one thing I want to tell you that these Northwest windstorms are what we call mid-latitude cyclones. Here's a picture of a mid-latitude cyclone that I swiped from a 101 book, okay? And there's a low pressure center in the center. And these lines here are isobars, so it's low pressure here and higher pressure around it. They're often associated with fronts. This in this case a cold front and a warm front. Okay, so there's often fronts with it, so there's something called an included front, but they have a low center. Okay, and the strong winds are associated with the low center, but not in the middle of the low. The lower the pressure in the center, the stronger the winds in general. Okay. Now we get low pressure centers coming off the ocean every winter, many of them, right? And the typical low has a central pressure of maybe 990 to 1,000 hectopascals. A moderate storm maybe 980 to 990, but the strong winds are like 950 to 980. Okay, so. Most years we can never get down to these 950, 970 at all here coming in. So the deep lows, they have low pressure, and the lower the pressure, the bigger the change of pressure around. The bigger the change of pressure, the stronger the winds. That's what drives winds. Difference in pressure drives winds, okay? Did I hit that hard enough? Yeah. Okay. Now the other thing I want to mention is, right now we have weather satellites. And we can see these, we see them off in space, beautiful. And you can see the scale of this. I mean, they're huge. I mean, just to impress you, this is the inauguration day storm. You can see that you don't have to be much of a meteorologist to know the lows right there. It's a cloud swirl to the center. But this is a big scale. Look at this one over here, It's Vancouver Island. These things are, these things can be 1,000 miles easily. Now, are there anybody from Florida here or from the south? Okay, well, you may want to leave. Florida, you get hurricanes, but they are just tiny things in comparison to our cyclones, right? Ours are big, right? Really, they're much bigger. The scale of these are much, much smaller. I mean, this is Florida over here, and it's just part of Florida. It's the island. Okay, now our cyclones are what we call our oceanic cyclones. They're oceanic cyclones. It turns out cyclones have a different structure over land and water. It's kind of interesting. And there's all kinds of studies about how cyclones look over the ocean. Well, I want to get to the bottom line about this. Okay, I want to show you what an oceanic cyclone looks like. And this is a model simulation of an oceanic cyclone. Now, this may be hard to see, but the shading, this shows you the sea level pressure. Here's the low here. In the oceanic cyclones, they tend to have a structure that the strongest change in pressure is to the south and to the west. So actually the winds are quite light in the middle. If you want to escape the winds, just go in the middle. Okay. The strong winds are where the pressure differences are. And they tend to be to the south and west, okay? Southwest here. And in fact, it's hard for you to see. I know this is a pressure pattern. The shading indicates winds, and this reddish and white stuff are the strong winds. The lows there, and here's the strongest winds that are to the south and to the west. Okay, that's all I want you to know. Okay, and that's a typical oceanic structure. So you don't want to be south of the low. It's much better to be north of the low, because that's where the strong winds are. Some people call it, there's a name that some people given in the field. This is the poisonous tail, the bent back occlusion. Tom may have heard this one before, but anyway, the oceanic cyclones, you don't want to be there. Okay. Now, to get strong winds here in western Washington, you want the low to go up the coast and cross over the tip of the Olympic Peninsula or Vancouver Island. So if you look at all the big storms that have given the really big winds here in western Washington, they all have the same tracks. They start out here and they come up the coast like that. And why do you want that? Because you want that southern part to come into you. That's how you get it, right? If it goes south here, you don't get into that. If you want to get that poisonous tail part, you need the low going north of you, right over there. Okay? So when I'm forecasting, I'm always looking for a low coming in. So should I hit it hard enough? This is your 101. Okay. I mean, I should do an exam at the end. But that's what you want. You want the low coming up the coast like that. And that's what gives the strong winds. You have forks down south and on Seattle. So the low goes north. Yeah, like this. Yeah, this is an example of a very strong system. And there's the low, and there's the big change in pressure, and that was going to destroy the coast of Washington. Now, there's another reason that these storms are really a big deal here in the Northwest, is we have a force multiplier. What's our force multiplier? It makes the damage way worse here than in Florida.
Topography.
What? Not the topography.
Trees.
They help the trees. The trees. This is the home of one of my colleagues, Professor Bob House. And he was out there with his daughter looking at the wind. And at that time, the trees started coming down and they ran for it, right? Well, let's say there was that truck never was the same. But we have these trees, and the trees cause massive damage around here. Yes, our friends in Florida, what do they got? You know? I mean, it's not the same, right? Right. We have a storm season. And they, the hurricane folks, they have a hurricane season, late summer, early fall. We got one as well, but it ain't then. It's November to February. And that's when these cyclones are strongest and coming in the right track. So November, December, January, February are the big months. And it turns out some of the biggest ones have happened in October. The Columbus Day storm was in October. So, it's starting in October and going through the winter. Then once you get to April now, the season's over. Okay, so you can relax right now. Okay. So one thing I'm going to brag a little bit. We have made extraordinary progress in forecasting the storms. We get virtually everyone. Day or two before, sometimes much more than that. We don't miss any of them. Like zero. It's unbelievable. And I can meet you back to that last big one back in 2006. It's even in the Seattle Times. Why are we so good? What happened that made it that we get virtually every stuff coming off the ocean? We get them all. What? Anybody know? Satellites.
Bigger computers.
We have bigger computers. Our computers are better. We can run at higher resolution, but that wouldn't have been enough. We need to know what's happening on the ocean, right? And you go back to 1962, and we didn't even know that. And so, but now the most important thing is weather satellites. Okay, we have satellite data, multiple satellites, and it's just increasing. So that's sometimes if you want to know what a TV meteorologist doesn't know what they're talking about, something you'll see them say, "Oh, it's hard to forecast the weather here in Seattle because we don't know what's happening over the Pacific Ocean." Right? You ever heard that one? Oh, you can't forecast here. Well, they don't know what they're talking about. Because we have absolutely massive amounts of data over the ocean. And so we have that, plus we have very good computer models. In fact, that's what I do. I'm a modeler. Okay, so we have these computer models that can have a lot of physics, that have a lot of resolution. Starting with all the satellite data, we can just nail these storms one after the other. We don't miss them. That's a tremendous accomplishment of our species. In fact, we can do this, right? By the way, one interesting thing, that Columbus, the Columbus Day storm, right? Remember we didn't, that forecast wasn't that good? Well, I went back and redid it. I reran the model using the absolute state-of-the-art model. I couldn't get it. I couldn't do it because the data offshore wasn't good. And I tried. Okay. Okay. I want to talk about something that the media is just crazy about. You hear this term bomb cyclone?
Yeah.
The media discovered this year, they're going nuts about, right? Bomb cyclones. These are mid-latitude cyclones. They call them bombs, right? And in fact, this was a big bomb year for the Northwest, right? You'd have to be dead not to have seen some of the coverage of the bombing, right? In fact, we had during November, we had this extremely intense cyclone that came, right? And it didn't come in here. It didn't follow that special track at all. The cyclone stayed offshore, but it was down to 940 something hectopascal. I mean, it was unbelievably intense, but it didn't come inland. And so this is the bomb cyclone, but it did produce very strong winds, but not here on the coast. It produced it in places like on the foothills of the Cascades, and places from Enumclaw up north to Black Diamond, and then up to Issaquah. Okay, and the reason for that, and you can see this is a pressure analysis here. Those are isobars, lines of constant pressure. You see that big change there? Tremendous pressure gradient. The low offshore held, but there also was cold air and high pressure inland. And between them, a hyper pressure gradient was created that produced really strong winds that descended down the western slopes of the Cascades. I went there afterwards. I couldn't get in. So bombs. I mean, it was unbelievable happening. Okay. I mean, my house in Seattle, the winds were off for 3 days. Okay, so now when do we use the term bomb? This meteorologists have been using this term for a few decades now. And we use the term bomb for explosive cyclogenesis, when the pressure changes by 24 hectopascals in 24 hours. Okay? So the pressure falls by that much. There's some latitudinal stuff. I won't get into that. Then we call it a bomb. Okay. And the one that was offshore, that intensified very rapidly offshore, and it was a bomb. Okay. So it's bomb cyclone. Okay. So the media is just crazy about it. The Seattle Times kept using bomb over and over. Okay. Okay, now the controversial part of the talk. Every talk needs a controversial part, right? Will northwest cyclones increase in intensity under global warming? What do you think?
Yes.
Yes.
I have my doubts.
You have your doubts. Well, you're right. It's good to have doubts. The answer appears to be no. These cyclones are not increasing due to global warming. There is no observed increasing trend in these storms. None. The climate models, and I run climate models, and I look at climate models, they're not doing it, okay? And in fact, we got a contract with Seattle City Light. They wanted to know the answer to that. Me and people in the climate impact school at the University of Washington, we did a study, okay? And we came to that conclusion. The answer was no. And it's kind of interesting. This shows you the maximum wind gust at Astoria. And over here, the red and sustained winds, the blue, and that's 1970. And I don't think I've impressed you because of the trend. Okay, and then we looked at climate models. And we run high resolution climate models at the University of Washington. And there was no upward trend, okay? So the UW Climate Impacts Group had a report and basically for the 1930s and 50s, most regional climate models suggest a slight decrease in the number of valleys, okay? So that's probably not significant. So the answer is no. It doesn't appear that this is, you can be worried about stuff, but this is not one of the things to be worried about. Okay, well, I think I'm gonna end my talk now because I want to keep it down to 40 minutes. And now I want to do what I really want to do and answer questions, okay? And I'm happy to talk about these windstorms. I'm talking about anything about Northwest weather and climate, and I'll even get to anything more controversial if you want. Okay, so this is the part I really like. Yes.
So maybe this is a stupid question, but the shape of the cyclones over the ocean that you showed, it reminds me a lot of like turbulence going around things. Is it related to that at all? Or
Well, I don't know about turbulence.
not that one, like one of the previous ones.
Do you like the satellite picture?
Yeah, that one.
Like this?
No, the forward. One more.
That
Yeah,
one.
that one.
Oh, this one.
Like the turbulent flow off.
Well, I mean, this is a wave that's amplified.
Okay.
Okay, I mean, you are having, I mean, maybe you're partially correct here, or correct. That, basically we start with this is temperature here. We have a change in temperature and a wave forms on it. And it amplifies and kind of breaks. So in some sense, it's, that's correct. Kind of like a turbulent. You have an amplification and then breaking everything.
That's just reminding me of the shape.
Sure. No, that makes a lot of sense. Yes.
You told me about the satellite data. Do they do temperature and pressure gradients? Do you have any service calibration that's used?
Well, we can get temperature. We do get temperature from satellites. I mean, on TV or something, you'll just see a picture, right? But we got much better. We have a CAT scan. Yeah. We can look down in infrared and microwave wavelengths, and we can actually get the temperature variation in the blue. Okay, it's even better than that. We have we can get temperature and density structure by using GPS satellites, right? Everybody has you have your phone, you have GPS, right? You're picking up the GPS satellite, right? Well, we have other satellites that can pick up this the signal from the GPS satellite, and as the signal gets bent through the atmosphere, we can actually get the structure of the atmosphere from it. It's tremendous. We have satellites that are dedicated to this, called the cosmic satellites, and then now it's possible that we may be able to do this on steroids. You've heard of Elon Musk Starlink satellites. Well, if we put receivers on those, they can receive that. They can receive the satellites could receive the other satellite signal, and we can get this structure of the atmosphere all over everywhere because there's so many Starlink satellites. A whole nother level of detail,
Including pressure.
Well, no, it's not getting pressure directly. You're getting temperature, you get temperature, humidity, and stuff like that. But you can calculate pressure from that. If you know how temperature varies, you can get your own pressure. Yes.
A little anecdote about the Columbus Day storm. I was, fall 1962, my first quarter, University of Washington. I turned out for crew.
Really?
Yes. And that afternoon, John Bissett, the coach, came in and said, "We're not going out today. We were just getting started. We weren't even in the shell."
It was on that day.
Yeah, and he came in, "There's something going on to the south of us and we're not going out today." This was. Because apparently, the winds had hit down in the Portland area.
Yeah.
And he said, "We're not going out today." Sure enough.
Yeah. Well, that was why. I mean, there were reports that were coming up. That saved a lot of lives because it was clear something crazy was going on to the south. And that information got up to Seattle. And a lot of people were warned that way. Something unexpected was moving up the coast. But that doesn't happen anymore, folks. Very good.
Yeah, so I was the one who said yes to the intensification under global warming. So you were talking about how it was difficult to hindcast that one storm. Is it possible that the models, you don't have enough years of models to accurately forecast decades into the future?
Yeah, I see, because it's a different problem. It's not a problem. Because it's not like we're trying to do a forecast, like initializing at a certain time and doing forecast forward. We're running the model freely into the future. And so it's not, we're not trying to get that exact forecast. We're trying to see what's the statistics of the kind of storms that develop. And that we can do. And it just doesn't show it. And in fact, I'm running, my department, I have this regional climate project. Gosh, I'm running like weather forecasting type resolution. And we just don't see it.
So just as a follow-up, I mean, there are stories about, various storms around the world and how it appears that there is intensification. Is it just this region that you're doing those forecasts for? Or you don't think anywhere in the world they're gonna be more intense?
I don't think any of these type of storms are getting more intense. And I know the literature, so I'll tell you, these kind of storms,
Okay,
no matter where Europe, Southern Hemisphere, they are not getting intense.
Could you sort of give your understanding, in layman's terms of what is it about increasing temperatures that lead to them not increasing more? Is it that there's less cold and the cold is actually part of the energy difference? Is there a way that you can sort of just give a rough explanation that person can understand it?
Sure. That's why I get the big bucks. I'll try. Okay, I think I can give you something that you find satisfying. The energy source of these storms is the north-south temperature gradient, right? You accept that part, right? Well, global warming is bad for business because the Arctic areas are warming up more rapidly.
Yeah,
That's
right.
so that's the reason.
That's
So
the reason right there.
that's gonna be weakening the north-south, the low-level north-south temperature gradients.
So that's the take-home message, really. I mean, because I was a physics major. It's not that I can't understand, but
So was I.
looking for your Yeah.
Yeah.
The altitude, the Arctic is, yeah,
So that, I mean, that's one thing that could be working against. So all I can tell you, I think there's, we've already experienced some global warming. And there's no increase. So, I mean, if it was sensitive to global warming, we would know that. And so observationally, it's consistent.
Could these go down then? I mean, if there's less of a gradient in temperature?
Well, I'll tell you why it's more complicated. Yeah. The temperature gradient at low levels is decreasing, but it turns out the high levels, it's increasing. And so you get the two kind of fighting each other. So that's why we're not ending up with not much of anything, because we've got two countervailing effects. All I can tell you, I think it's a very robust finding. Yes.
We have a
So-
question online.
Oh, okay.
Sorry, just
Okay.
a quick question online.
I'll go back to you.
Okay, thank you. This is from Timothy Gray. They say, I was born and raised in Hawaii 50 years ago, and it amazes me how we dodged so many hurricanes. Why is that?
That they got a lot of hurricanes?
That they dodged them.
Oh, yeah, okay. Oh, they dodged them. I feel better. Well, it turns out that Hawaii is not a good place for hurricanes. Because the water's too cold. You think it's Hawaii's warm water, it isn't. I got the kids, it's kind of, the water, it's not the Gulf of Mexico. The Gulf of Mexico is way more than the water around Hawaii. So the water around Hawaii is very marginal. And so they don't get hit by hurricanes very frequently. I mean, it has happened, Yiki, and, yeah, I can think of a few others, but it's relatively rare. So it's the water, the key thing is the water temperature. Very bad. You have a question?
I'll give you an observation, you tell me if I'm full of hot air, but, you know, I came to Forks in 1970 as a new forester, and the remnants of the 1921 storm were everywhere. Everything west of basically 101, that rolling flat ground out there, 21 blow was everywhere.
Right.
Those stands regenerated by themselves, they came back real thick, dog hair. And so, the 62 storm I don't think had much of an impact. Really, there was no talk of, oh, that's a 62 storm plantation there and so on. There wasn't much like impact. My theory is, you know, if you sat on a hilltop and watch some of these events come, all that was impacted west of 101 by the 21 storm were all thick young stands.
Yeah.
And windstorms hit that, if you've ever watched it, and it's like a magic carpet.
Yeah.
You can't get down in it to shove.
That's really interesting.
Across the top.
That's
And so
fascinating.
62, we had a lot of those younger stands at that time from the 21 blows in the most vulnerable areas west of
Yeah.
101. There was not a whole lot of impact.
But it was not nearly as intense. It really wasn't as intense.
The storm is very big, but I can tell you, it knocked down over 750 million board feet.
Yeah.
In mostly the whole Clearwater.
Yeah.
That was a big deal. But, you know, there are storms, and that was inland in old growth, broken, rough ground.
Yeah.
21 blow quit going inland because it hit topographic shade.
Yeah.
And it just, you can see those, it finally just started taking the ridge tops and then it petered out because of the topography. So anyway, just an observation, and it just from watching some of those stands hit, it's gotta get behind something to blow it over, and I relate only to how it impacts standing timber, but that's just what I kind of think was going on.
Well, that's very interesting, very interesting. So the other questions, yeah, go ahead.
I was gonna say earlier, so if you're having these evolving, differentials up in the, you know, in the upper atmosphere versus lower atmosphere, is it possible you're gonna see like some different sort of storms come out of that maybe isn't related to, you know, latitude cyclones, but is still caused by the warming effects?
The the models are pretty clear, even when we hit it really hard, that you don't get stronger than latitude cyclones. So that's pretty robust. Tropical cyclones are a different story, because you know you are warming the water, and so some of them more extreme. You know, tropical cyclones could be more extreme, but not the mid latitude ones don't seem to be. Yeah, I mean nothing's perfect, right? I'm giving you a climate-based forecast, but virtually every modeling system is there.
Is that why we want to move out of Florida?
There are other reasons.
I don't know. This is a bipartisan. You had a question.
So, as data improves and computational strength increases, so you're able to improve your models, what do you expect? How long in advance do forecasts be able to be accurate in the future?
Well, that's a very interesting area. There's another revolution, which I didn't go through the technology of forecasting, but there's a big revolution that's happening right now in machine learning. So machine learning. So basically the way.
Lack of willpower.
I don't know. Okay.
Sorry.
So. It doesn't have anything to do with willpower. Anyway, the traditional way of forecasting is you get all this information describing what's going on right now. And that's called the initialization. And then we have these computer models. I mean, they're not like a model going down, you know, it's not like a model. It's basically we have the equation to describe the physics of the atmosphere. And they're predictive. If you know what's going on, they have time to read it. And then allows you to see what the future's going to be. Okay. So, I mean, that's the classic way of forecasting. That's, you know, I do models. That's how I do it. Okay. But there's another way that we're starting to figure out how to do that. We get this description of the atmosphere, and then we can use machine learning. So it has, you know, it has history of what's happened, and it can be trained on that. And then it can start with what's going and then tell you the future without the equations. So this is something that's turning out to have a lot of promise. And so it's a revolution. And we're not so far, we're not sure how far it's going to go now, but it seems to be able to go pretty far. So that's the next revolution. So your question about what's going to happen, higher, no matter what, we have computer powers increasing, we can have more and more detail. But there's something else we can do. We can stop lying to you. And I'll tell you how we do it. If we give you just a forecast, the temperature tomorrow is going to be 75. Well, the temperature in 2 weeks, in 7 days, be 86. That's ridiculous. It's all this uncertainty, right? So, and the uncertainty increases with time. There's theoretical reasons to think that our ability to forecast the details of weather only go out about 2 weeks. And it's based on chaos theory. Remember this chaos theory. Anyway, so the fact is, there's another technology we're developing very rapidly called ensembles. What we do instead of running our computer simulations at once, we run it 50 times, 100 times. Each one slightly different. Each one starting with a reasonable start, okay? Or have reasonable selections of the equations. Each a little different. So we can end up with a whole collection of many forecasts. That's one ensemble. So let me show you how you can do it. If you want to get, well, what's going to be the chance of rain in 10 days? Well, half the models, say rain, half say no rain, 50%, right? But you can do this with everything, temperature, humidity, everything. You can get uncertainty. You can get probabilities. So the big change in forecasting, if we're honest with you, we'll give you the probabilities. So I think that's going to be a big area of is giving probabilistic forecasts instead of saying this is what's going to happen. It is true. I think we're going to gain more skill in weeks 2 to 4. It appears now that there are ways we can get more skill. At least generally what's going to happen. So I think you can see that as well. So we have more to do. Yes.
Do they still do the weather balloons out there?
Yes. In fact, I was going to go out there.
Oh, and
This is an important observation location. Is right here. The radiosonic clue. Right. So I don't know if anybody ever found a balloon coming down. You found it?
Oh, yeah. Different cruiser. Yeah, I found 41.
Well, in fact, there's a website you can go to. Well, I live down here, I do this all the time. There's a website that tracks them, and you can find exactly where they fall. So if the winds fall here, the winds would have to be pretty low. But right.
Whidbey Island is where they fall.
What?
Whidbey Island. There's a lot of them.
It'd be further down, but yes.
About what he said, you were talking with him about the satellite data and so forth. And with the satellites can do now, as far as dissecting the atmosphere and the vertical and so forth. What are we getting from balloons that we're not getting from satellites? Because I'm hearing buzz in the weather community about the loss of the balloons and how it's going to hamper forecasting.
Right.
And you're talking about looking through the vertical of the satellites. What are we getting with the balloons that we're not, or are we going to? Is there something in the future coming soon that will take place in the balloon?
99% of the data that we use for weather predictions from satellites. And there's something else about the balloons. We have another technology that's giving us very similar information when the aircraft, a lot of aircraft taking weather observations, and they come in and out of airports, you get observations, and so it's almost like a real thing.
Virus.
Yeah. So, or not this, even better than that. You know something about this stuff. Okay.
I was in the field for a few years.
Okay. So, okay.
Yeah.
Yeah. In fact, there's Pirates that's manual, but we actually have automated systems.
Oh, nice.
That give us that information. The radiosondes are not as crucial as them. That's undoubtedly true. But what they can be used for is we can use it for calibration purposes for the satellite.
Good point.
So and it is used for that because the satellite, it's good to have some calibration.
Very good point.
So the balloons are,
They're not out of date just yet.
well, if we didn't have any of them, we'd be functioning. I'll tell you right now. And you might not even notice it. But at this point, we're not ready to give them. Yes.
So I grew up in Baja, we got a bunch of hurricanes there. Baja in
Baja.
Mexico.
Bob,
And, but the main damage that they cause comes from water, from all the precipitation of those storms. So I was wondering if these storms also bring very strong precipitation, is that gonna cause some changes in precipitation patterns? If they slow down or?
well, these storms generally, they can produce some precipitation. But they tend to be, but if they're moving too fast. And they generally, precipitation is generally not the main issue. For us here, the main precipitation issue is atmospheric rivers. That's what reduces. The heavy precipitation that causes, substantial damage. And disrupting flooding and all kinds of bad things, right? So atmospheric rivers are the main precipitation issue. These storms, precipitation is not the main. Yes.
So, what year did the open ocean data start, coming into play?
We started getting it in the 80s, but it really took off in the 90s. Where we started getting massive amounts of stuff, and we also learned how to use it. There's a technology called data assimilation, and we've got much more sophisticated in the use of that data. So the 90s is, I may have another talk I could give on the revolutions in weather forecasting, and I talk about that.
Well, I was curious because in the 70s, in the Pacific, we got caught in typhoons.
Right.
In the Atlantic, we got caught by hurricanes. We had like a day's notice.
Yeah.
And our weather guessers were, working their butts off. You get this stuff from Hamo or Norfolk, give us the data, but still, you can't run those things. So
So
the
that
80s.
No, but it was like, the 80s we were warming up, it was really the mid-90s when things really took off. In fact, in some ways, we're so good now, we get less observations on the ground than we used to get, because before ships used to get caught and stuff. Now, big container ships, they know big storms, they avoid. Beautiful.
So yeah, I've spent some time studying stand development from historical windrows up and down the West Coast. From Oregon to Southeast Alaska. And it's my experience that there's more evidence of really big historical wind events in Southeast Alaska, particularly the north part of Southeast Alaska. And I'm curious if there's some physical reason for where the peak damage could occur if you went from California to Southeast Alaska. Could it happen anywhere in there? Is some place, are we the peak here?
Yeah, well, that's a good question. I don't know the answer to that. I mean, we get these storms, but our storms are child's play compared to some of the Gulf of Alaska storms, which can be much deeper. So I suspect, I'm not an Alaska meteorology expert, but I would suspect that they get hit by some storms that's shorter.
That's what it appears to me.
Because I know what the pressures are like, and those storms can be extraordinary, more, they can be more intense.
You're 920 hectopascal.
Yeah, just 920, 930. It's gotten that low.
I spent a couple of years meteorology on Adak Island. So
Did you?
I can confirm what you just said. They get a lot more severe, and whether the storms we get here are child's play by comparison.
Yeah, well, the Gulf of Alaska is definitely that thing.
Yeah, it's crazy up there.
Yeah, I know.
It's crazy.
Yeah, they get much storms.
Yeah.
Yes.
What about the trajectory of the storms? Is that, you talked about that sweet path.
Yeah.
Is that gonna get more?
We haven't seen much of a trajectory change. I looked at that, I was not much. Yeah, in general, for all storms, all the standards. Yes.
I spent some time talking to, forest growth modelers in my career, and we would make predictions for our investors about what the volume would be in 30 years from now. 10 years from
Yeah.
now. Frequently it was wrong. And a student at the University of Washington, I think a graduate student, told me one time, all models are bad, some are better than others. So if we can't predict the weather out accurately in 2 weeks, how do we know that the models looking at the relationships going out into the future are in the ballpark?
Right. It's a different type of forecast. In the technical talk, it's different between an initial value problem and a boundary problem in simulation, right? So one thing is initial value problem is when you're trying to get, the exact position of that node, exactly what's happening. And we lose scale. The small uncertainties, build up into them. When we go out, we run a model for, these climate models, we're not trying to do that. We're trying to get the statistics right. So it's a completely different enterprise. It's not, it is alluded to. We can run these models and get the climatology right. Even though we're not forecasting the years. You know what I mean? It's a different thing.
I have a question.
Okay.
Go
ahead.
A few years ago, there was talk of doing some research using cell phones to track atmospheric pressure. Has that gone anywhere?
That's my project. So that's the work I was working on. I've been working on. So anybody have the Weather Channel weather forecast app? Good. We're going to we get it actually gets you pressure. those apps are getting pressure. Supposedly you're asking, it's okay. So we're getting pressures from the smartphones, which allows us to fill in, details. And so, for instance, we're getting like 1 million pressures a day from the smartphones. And so I have a project, we've shown that we can improve forecasts locally with that. But right now I'm working with NOAA to try to get into their forecast models. The pressures from smartphones and other things can be improved forecasts. So yeah, so anyways, we're working on it. This is the whole area called crowdsourcing. There's all these other types of observations in it, but it's more than that. I mean, you get your smartphones have pressures, okay? A lot of people have home weather stations. Can we get those together? Right? A lot of them have weather observations. Can we collect those together? Right? There's air quality stuff that has pressures, so we can get those too. So we can get these massive number of observations. So the world has completely changed with surface observations. If I put you in a time machine back 50 years, there was only maybe 1,000 surface observations in the whole United States. Right now, it's a million from all kinds of different sources. So we have much more fine-grained observations of the surface than we have, right? Because the internet's everywhere, these cheap weather stations everywhere, smartphones everywhere.
Thank you.
Who hasn't asked a question? Okay.
So, not far from here on the lower Queens, I go in fishing. And there's one area that just gets hammered by the wind.
Yeah.
It can be a storm, a decent sized storm or a big storm. I go in there after, and there's trees everywhere. You go walking along the Salmon River, and they're like matchsticks.
Yeah.
Big trees. Is that because of the storms are coming down the valley? Winds coming down the valley, or what's making that?
So what's the terrain like in that area?
It's generally a lot of rain.
Terrain.
No, the terrain is flat.
There's no terrain.
Oh, I'm down like right along the Salmon, and if you walk from this ridge of the river down to the Queens, it's like blown down matchsticks. We had that storm in December or January, and big trees You came down and you look and they're everywhere in there.
Well, I mean, the thing, terrain can accelerate winds. Wind is stronger over the water than it is over land. So if you have a better fetch over water, you can get stronger winds, you know, that can do it, right? There's a limited number of things that can do that.
It just seems like it's a
localized.
consistent deal, like year after year.
You have to show me a map.
Yeah.
So.
Yeah.
I kept wondering why, I always thought that this big storm of 1979, when the Hood Canal Bridge came down, was one of the biggest, but it wasn't even mentioned. So was that kind of a localized event?
Yeah, okay, I can answer that. In fact, the answer was in one of the figures I had already. Strangely enough, there it is. Okay. The Hood Canal Bridge is right there, right? And what happened was, the winds weren't from this direction. They were a little bit more from this direction. This low moved over there. The low was over here. So the intense pressure difference here moved right over. So what happened is that there was a windstorm that day.
Yeah.
Coming off the Pacific. You know, it was kind of a garden variety, right? So maybe the winds were, 15 miles per hour on the coast. But then, because this low was over here, and the intense pressure gradient was over here, the winds accelerated even more, and the winds got to over 100 miles per hour. And that's what took it down. They also did some stupid things like leaving the manhole covers open. And that was, that cost us a lot. Any other questions? You asked, is anybody else? Okay, go ahead.
A little bit off topic.
Oh, I know.
We hear a lot, about average global temperature.
Right.
And predicted changes in average global temperature.
Yeah.
How is average global temperature calculated?
Get the temperature over the whole planet and you average it out, geographically, you average the whole planet, the planet, right? And so you can get that kind of average, right? Or you can get a certain location, you can get time averages, right? So the average temperature, we know what the temperature is everywhere, right? So we can just average the whole planet and we know what the temperature is and we can see whether it's warm or cool.
And how do we know what the average global temperature was several hundred years ago?
Well, that's an interesting question. I have one of my colleagues works on that. I mean, obviously, we don't know it as well as we know it now. That's true. This is an area called paleoclimatology. And one of my colleagues, Greg Hager, he does this, okay? So what you do is you get to connect, you do have some things that you have back that far that are related to temperatures. You can look at tree roots, with that. And there's other things. There's a number of indirect measures, right, that you can use to get localized temperatures and how they change. Then we have these paleoclimatic models that are able to take that information and try to just use that to describe what the temperature of the planet is like. Okay. Now I'm not going to tell you that it's as good as temperatures are now, not, but that's how people do it. There are some places that we do have hundreds of years of temperature in some locations. We do have it in a few locations, but it's certainly not really. Okay, you can. Last one. This guy has questions.
So when you're talking about your project with the crowdsourced phone data, is that based on like sensors inside the phones, or is that from like the GPS signal estimation that you talked about?
No, that's the sensor in your phone.
Okay. Is there any?
The phones actually have some pretty good pressure sensors in them.
Is there any like movement in using the GPS data from the phones, like that?
Well, GPS is important. We get the pressure, and we know who you are.
Right, but you said
we need both.
The satellite GPS signal.
That's something else.
Okay, but I'm saying, like, is it possible to use the satellite phone GPS signal in kind of the same way?
Not that I've heard. But not that, yeah, no, I haven't heard that, using that to try to figure out temperature structure. I'll think about that.
You said that satellites calculate pressure off the temperature. So
If you have temperature, you can figure out pressure.
So your phone would be different if it was in your pocket rather than sitting on the desk, right?
Well, you're not gonna use the temperature of your phone.
To calculate the pressure.
No, you don't wanna use you have actually pressure in the phone.
I see.
Use the pressure, which is much better. The pressure outside of this building and in here is not gonna be very different. Because we have that door open, right? So as long as you have a leaky room, then the pressure is not gonna be very different outside and inside. So the pressure inside that, in here is very, very much.
Well,
Okay.
on that note, and I think Cliff will stay a little bit after, thank you all for coming very much. The next